Okay, so welcome everyone. I'm very excited because I think we have prepared a very exciting panel session on AI testing. So overall, the automotive industry is not immune to the AI revolution, and we see more and more AI adoption as a part of the perception, decision-making, validating performance, and so on. We used to have some traditional validation techniques for software where we would do coverage analysis, this kind of things, but obviously everything is changing. So this panel is bringing together a different perspective for a deep technical discussion on how AI validation is evolving in practice. When failure occurs, how do we decode the origin of the issue? I think it was related also to the previous talk. It's very difficult sometimes to understand why the AI is failing, what are the real reasons, and then what do we look, what are the testing strategies, and so on. So I'm Professor Valentina Donzella from Queen Mary University of London. I'm really glad to chair this discussion, and I would ask the panelists to introduce themselves. Martin, do you want to start?
Yes, good morning, everybody. My name is Martin Stoffel. I'm working for TORC Robotics. I am responsible for the platform software in TORC, so meaning the base operating system itself, but also the middleware. And here, I think for this discussion, relevant is also our GPU-centric middleware, which we use to operate our machine learning models.
Thank you.
Hello, everybody. Good morning. I'm Devin Wojcik. Glad to be here. I work for MHP. We're a company that helps our clients in the automotive manufacturing space handle different challenges within the business. My background is in automotive engineering, specifically supplier and kind of software-defined vehicles. So I look to how do we move that forward for our clients. So.
Good morning, everyone. I'm Praneeth Nelapati. I'm from General Motors. I represent the AV Sensors organization, responsible for both hardware and software side of the perception.
Good morning, everyone. My name is Venkat Adsumalli. I work at Stellantis. I'm responsible for core platform services on the SDV.
Okay, thank you very much. I have a few points for discussion, and I think where I would like to start is how is AI increasing the complexity of end-to-end approaches, testing approaches, and how we establish when virtual validation is enough and adequate. So if I can start from you, Venkat.
Yeah, the main challenge in the validation in various environments is the correlation that we are trying to bring in with the real-time scenarios. So for example, this is often we see from different test teams, even whatever the software we release, and everyone says, it works on my bench. Or like the other hill guy says, yeah, it's not working here. Like, and when I speak to my developer, like it says, yeah, it is working on my bench. This is the common scenario. So the idea here is, and the complexity increases with the AI. Like AI is not really a simple coding problem. It's more of like a data problem. So even though the data used in different validations in different environments, like a vehicle in loop or hill, that they really vary from the real-time data, because we train on data and we use certain data, simulated data, to test, but whereas in the real world, it's completely different. So the biggest challenge I see is the correlation. So how do we bring the real world scenario into these environments is the biggest challenge, in my opinion.
Anyone would like to add something? I'm thinking about you, Martin.
Yeah, so a way how we tackle that at TORC is that we are capturing data, of course, on the streets, deriving scenarios from that. And then we have the problem, like how many scenarios are actually enough scenarios to finally say, yeah, we are good, we can send that vehicle on the road. And one option we have here, or which is common in the industry, is a generation of synthetic data. In a sense, we take the scenarios and we generate edge cases coming from there. And here also in particular already on the raw data side of things. So not only in the behavior stack, but we are literally creating like visual, if we would take the camera as an example, visual synthetic created scenes with which we feed then into our system to kind of close that gap you were talking about.
Sounds good.
Yeah, maybe I'll just talk about it from a perception standpoint. I think the biggest challenge that we've seen is the deployment speed has become pretty critical because every time we see a certain new feature coming up, especially with the AI, ML side of the things, the feature space and the kind of data points that we are looking for have become very unique. It's not about spending the number of miles on the road. It's becoming trying to gather the exact specificity that we need to go for. And there's also the developer bias that we are getting into, which is they're always trying to solve the problem that they're projecting, which also can give us a very different point. Like we could spend a year trying to validate this system, but once we deploy it, we find this very unique event that is maybe 70 to 80% in the same space that we've designed, but something changed, maybe context or maybe the kind of like events leading to that, and that kind of completely changed the CI/CD pipeline. So that has become almost a very unique challenge that a traditional deterministic processing chain have never encountered in the past.
Yeah, and I mean, even if, like we were discussing before, we design the ODD and so on, which obviously to me is a starting point from a perception perspective, then you have the real world variability and everything is skewed, and even a slightly variation in the colors that you have in the environment can completely change. And I don't know, I still think we don't have that mathematical way of saying when we are covering enough the variety of the real world, and that makes it very difficult.
Yeah, the another point I would like to add is like when we are collecting this data very close to this, but it again the time when we capture this data versus like the time when system behaves, right? Like that's completely different, like how the sensors are behaving that time, and what is the latencies that are coming into the picture, like of the sensor data that is feeding into the model. So these are all different things, like we need to really, it's not just simply validating the model, it's about validating the entire system. And so we have to build certain mechanisms that can able to find out, okay, what is the trust score of the sensors, or these kind of things, different, like that's where I would focus on, because we at Stellantis, like from my team, we focus on logging data, like logging, that is a feature we provide to a lot of applications. So the amount of data they are going to log in, and the parameters they have to log in is the key in this case.
Yeah, and if I can add on what you mentioned about the data, I think we think about testing AI, but we don't think about certifying the data sets. Like we have NCAP scenarios and so on, but we don't know which are the data for which we need to test for. So that makes it challenging. Anything that you would like to add, Devin?
Yeah, absolutely. I think another aspect to this that makes it challenging is it's obviously a moving target. We're here, we see all these different technologies that are being presented. Things are changing daily, both from a sensing perspective, but an AI capability perspective. So it's a moving target for how we're actually going to handle the challenges. And then if you kind of look back a few years with this introduction of software-defined vehicles, where we have to look at this problem cross-functionally and not just into the singular functional areas like ADAS, chassis controls, and whatnot. So handling that data, I think, is a challenge, because it's already a challenge to look at it in the single functional domain. But once you look at it cross-functionally, it starts to become overwhelming, and figuring out a way to handle that data, process it, is going to be something that really drives success in the future if we figure out how to do that.
And I think when we were preparing for the panel, we also slightly touched on the challenge related to how do we manage the huge amount of multimodal data that we are harvesting and how edge intelligence plays a role into it. So I don't know if anyone would like to touch on that.
Yeah, I think, again, right, like the more kind of modules that we are adding as part of this is exponentially increasing everything. And I think the biggest impact that we are seeing, at least on our side, is the silicon usage is really getting impacted because of this. So trying to balance how much data you need or how much feature points you need to kind of is creating this challenge. Again, higher feature space is always giving us better results, but it's also creating these other issues in terms of inference and trying to understand what this physical AI is trying to get to us. And yeah, it's kind of creating this a very unique loop of where we are trying to validate as we try to design, which again is, I'll say, a new problem that some of us are facing.
Anyone would like to add anything, Martin?
Yeah, so I mean, data collection is one of the absolute critical and key items when we talk about a AI-defined vehicle or a software-defined vehicle. So we have a lot of sensors on our truck, and this is creating a lot of data. And we have a highly distributed system, so that means it brings challenges, for example, such as time synchronization. It brings challenges such as CPU utilization if you once you write the data off to a disk somewhere. And it's extremely critical because because we have transformer-based models in our system, we need to capture sequences. So that means, let's say we need a sequence of 30 seconds. If we just drop a single frame here, or we have a not functioning time synchronization, this whole sequence is actually waste. We cannot use it anymore. And that is a challenge which our engineers are facing every day. But there are options to overcome that. And that's what we do. And then the next step actually is to put all of that into the cloud and try to find the relevant scenarios for the models, which takes time, which costs money, and that is why we are trying to put this detection mechanism already to the edge. So meaning we detect if we drop frames, for example, and then we would not even write those stuff to a disk for later downstream usage, actually. So data recording is a science for itself.
Yes.
But an important one.
And if I can add that, actually, out of curiosity, we haven't discussed this in our preliminary discussion, but as a part of my research activities, we are also investigating data compression, data reduction in a meaningful way without dropping the key information or considering region of interest, region out of interest, and so on. Do you think it's something that should be considered? Or?
Oh yes, absolutely. Not only for training purposes, we have also fusion algorithms in our stack, early fusion algorithms. They also need data, and when you move this data around in a highly distributed system,
it's crazy.
It's literally crazy. Yeah. So data compression is also an important topic here.
Adding to that, like I think now the problem is more of like the scale problem, the amount of data that cannot be handled by the human anymore. Like I think we need to bring in AI for the validation as well. Like in this case, like for example, data compression, and we are trying to squeeze in the data that can be handled in a more deterministic way. Yeah. So there are, I think we are trying to validate the system. When bringing in the data, it's not about the amount of data. It's all about like covering to the risks, right? Like okay, the model is deterministic, but there is a slight amount of risk left. Like if we can build the data sets to counter those risks, that is where like we can effectively validate. So how do we do that? Like as a human, we may not really do that. Like our capability is limited, but we are good at judging, and also we can take the accountability. So bring in a lot of AI tools, create these synthetic data and these data sets that can actually cover the risk areas, and write thousands of test cases using this synthetic data to validate the AI models. That's where I think industry should go.
Yeah, and I think you also touched in something that to me it's very interesting, and we are hearing more about it, the hybrid intelligence, where you leverage the strength of us as humans and the models, because the challenge is the order of magnitude is too big to handle. Devin, anything that you would like to add?
Yeah, absolutely. I think that this is some great points here. I think one thing is having, because there's a bit of a chicken or the egg scenario here at play, especially when you're trying to innovate and say, I want to use AI in product development. Well, I don't have any data right now. In many cases, I think ADAS is very good with handling data, and you guys are fantastic at that. But other functions within the vehicle, especially as we go more towards software-defined functions, they don't have that basis of data to pull from, or if the data they have is not structured properly to be leveraged in an AI scenario. So making that plan ahead of time, and then being able to work through and collect that data, so then it then can be turned around and leveraged, because sometimes we don't have that data up front, or figuring out ways to create it or reformat old data in a way that can be used. So that's my perspective on that.
Thank you. Very interesting points, and sorry for going slightly off track, but yeah. I think the other point that we wanted to touch, and you mentioned this as well, Martin, is how is the SDV architecture changing, how we test and validate AI, and the data that we have available. So, David,
yeah, absolutely. I think I've alluded to it a few different times already in the conversation, but SDV, like this transition to software-defined vehicles and now AI-defined vehicles, really opens up the level of information that you can work off of and act on. So as I mentioned earlier, it's not just one domain is able to use its sensors in this domain. You can actually utilize those sensors that are in a cross-functionally across the vehicle platform, and actually really work off of it without large latencies and worrying about that. So when you have a more centralized compute structure. But that takes kind of re-looking at the problem, because originally we had to get creative and say, I have this one sensor that I can use and I need to act on it, and I can't consider that other functions across the vehicle are going to act on it. So rethinking how you approach vehicle controls cross-functionally is going to be crucial, and what that means is, what data do I now have at my fingertips and that I can act on, and then creating a control strategy that cross-functionally communicates and is all planned together instead of being planned individually. I think this can be crucial.
Anyone would like to add?
Yeah, just because you brought up SDV, I think one of the challenges that I'm personally facing in some of the areas is, from a scheduling standpoint, it has become almost like a little challenging, primarily because the unpredictability of the AI is kind of creating pipeline issues in terms of what to predict and what to schedule and reduce the latency that has been discussed about. Again, there have been methodologies at least reasonably working well as of now, but as this kind of really goes into new territories where we are decentralizing AI models for very specific feature sets and other things, and when they need to interact with each other, it requires a very special service-oriented architecture. Maybe SDV is the answer, maybe we need something else, but that is, I believe, the space that we are heading into. I just don't know the answer, but I'm pretty sure a lot of smart people in the room might already be thinking about it.
Martin.
Yeah, so that's an excellent point actually here, and this is like, let's say, cutting edge to the move from an SDV to an AI-driven vehicle, because what we have experienced is, when you build up a robotic system using things like the robot operating system, and I think many companies are using that thing, then you're running exactly into the problems which you are pointing out here. The robot operating system has an own execution mechanism actually, and there is a lot of research out there which tells that this is not deterministic and therefore also not predictable, as you just phrased. So I'm 100% agree on that. So now, what is our answer at TORC on that? And that is exactly this GPU-centric middleware I was just talking about. So we have developed a middleware in our company which is actually dealing with the stuff on the GPU. And the important thing here is two things, actually. Number one, we have to minimize or actually even avoid any kind of copy on the GPU. So when we have data as intake in the pipeline, we are just moving the data forward with a pointer actually and not creating copies anymore. If you use ROS, you would face copies. And then the other thing is we have an own execution mechanism which, let's say, maximizes the predictability of parallel or sequential execution of models. So for me, these are the two things where we then start talking about moving to an AI-driven architecture and leaving the domain of software-driven vehicle.
Yes, and I think there are a lot of discussion also in moving from software-defined vehicle to AI-defined vehicle. Do you think this is the future?
Absolutely. I mean, the question is, how do we call it? We can call it an AI-driven vehicle. We are kind of trial and error working our path towards the future. But yeah, so for me personally, a software-driven vehicle is actually an Ethernet-based system, distributed system, using, as you said, a service-oriented middleware. And an AI-driven vehicle is a vehicle which still uses Ethernet, but honestly, I'm not a big fan of Ethernet. I would rather go towards PCIe because it has a way higher throughput.
Yes.
Or ideally, we have so powerful SoCs in the future that we don't need any distribution at all. But that is a difference, like PCIe compared to Ethernet. And then the other thing is service-oriented middleware compared to, and I call that GPU-centric middlewares. Maybe there's a different name out there for that, but that's how I would describe it. So.
Sounds good. Venkat.
So right now, like what the service-oriented architecture, just going towards that, the SDVs do support the service-oriented architecture, and we are able to provide like all the data through the services. But the problem is like how we want to use that data, and going towards the GPU centric middleware. Again, I go back to again to the data, like where it's like it's not about the requirements we are going to cover. It's more about like the use cases, and then so the models are going to be run in a deterministic way. Again, the data what we are feeding in. That's determines the I would say the real world scenarios, like where the risks are there. So in a way, like I'm trying to correlate between the SDV moving towards the GPU centric middleware. What are the different, like I mean, like what are the different I don't know, like how to connect. So the I mean, like here, in a way, when we are trying to validate on the SDV, it is very simple. Like we have all these, like for example, whatever the data we have collected, and we are going to simulate through the different environments and provide it. I mean, like validate on the deterministic cases. But whereas in the GPU-centric middleware, the models are running there, and then the cases it is going to cover, I don't know, like how can we trust it's producing to the real, like closer to the real world scenario cases. That's where like the AI defined vehicles are still, like I can say, still far away because we cannot really, even though we are just going towards a heavily hardware dependent systems that can run the models, but it is not really building to the end use case. That's what I mean. I don't know. I was really able to connect these bit like the links, but what I'm trying to say is the real world scenarios still will be far away, even though we are advancing towards the hardware and the software models we are using. Still, that risk of not closing to the real world scenario will still be present. That's what my point is.
Yeah, and I think we touched it as well in terms of how do we include the data validity in the process as well. And another point that maybe you touched upon, and we can try and have a quick discussion, and then we might take some answers from some questions from the audience, is you touched about on requirements and the fact that we are moving more towards use cases, and in a way it was easier before because there were requirements. We could validate the system against requirements, pass or fail criteria, and so on. With AI, it's not true anymore. So how do we define test cases? What is the strategy from use cases to scenarios? Is there a way, an approved way, a standardized way to do that, or are we still far away?
Yeah, that's where I'm trying to go there. It's more on the intent side of it. Like, it's not just like simply a requirement validation. If I go towards that AI-defined vehicle, it's the model and it's the scenarios we are going to test. But how much ever we have provided the data and all, the model is going to, there is a slight deviation from the realistic world, because we are not really, we don't know, we did not capture all those things. So that's where I'm saying, like, there will be a slight gap, but we should have a different model to find out, to build the system and then validate the system.
Thank you. Any more points on this?
So I don't have an answer for that question. I guess nobody has an answer to that question yet. What I can add here is actually that the validation strategy is extremely important. So what we see, for example, is I think you touched upon the topic with the SDVs, that it works on that target hardware but not on that target hardware. Now there is one more level of complexity when we talk about AI-defined vehicles. What we have observed is it works in one location, but it doesn't work in another location. So how can you create a generic validation and release framework which finally allows you to say, yeah, that thing works? Yeah. I have no answer on that, but maybe some other smart people have that, or it's worked out in research at the moment.
I think it's an active research area, and I have seen some works on continual learning where you try and then teach the model to adapt to a new region and so on. But then at a certain point, you start seeing the performance that are declining anyways, or unlearning some previous learning. So it's a very challenging aspect.
I mean, what I like, just as a like a general direction or an idea, I say, I don't know if that makes sense in English so much, but a lot helps a lot. In a sense, if I test a lot of scenario in simulation, if I create a lot of synthetic edge cases in simulation, or if I run many and long tests in my target ODD, then at some point I should be able to say, yeah, that thing works properly. Yeah. But I will probably never be able to say it always works in any case all of the time.
I mean, but as humans, we don't work in all the cases, so we need to understand when it's enough. And in a way, to me, I think what you mentioned right now, the exploration, obviously, of your ODD, and then the boundaries of the ODD and creating some extreme cases probably is what we can do in a more systematic way.
Exactly.
Anything else from you?
Yeah, just to add on to that, right? I think we're at a place where we can't treat the AI models as a black box anymore. I think the developer-driven testing has become a little more mainstream because they need to understand how the feature space is actually progressing between these steps. Previously, we had the luxury of ignoring it, but I think we are at a place where we cannot do that anymore. And also, the bigger challenge here is how do we merge that with human intuition, which we can kind of backtrack. So I know a lot of industry folks are using a deterministic fusion chain in parallel to the AI chain to kind of cross-correlate. So maybe there is some answer there, but as the AI models get more and more complex, we move very far away from human intuition. So that will be the challenge on, hey, how much do we trust? Do we just leave it to the AI? Or do we put some safeguards? Because whenever I talk to my safety teams, they always freak out about that 1 in a million scenario that might happen. And they always want a good answer. Unfortunately, most of the times we don't have one.
Yeah. Touching on human intuition, we were actually talking during the panel yesterday about the fact that all this data, RGB data, radar, object detection, and so on, have been created for us as humans to understand, but in reality it's possible that we don't need all this processing. We just give raw data to AI, and then the paradigm is going to completely change. Any last words?
Yeah, I mean, I think it's important for me, from my perspective, it's always important, and we find this from the client, is how can we actually, shape the business and drive business success with these solutions? Because obviously they're super robust, they're super interesting and technical and fantastic. But how do we make sure we can bring a product to market faster? How can we make it more robust, make it safer? And actually quantify the learnings that we're all doing and working towards to, business outcomes is always important. So I think there's still, you said that we're a little bit further out, you said we're like kind of getting there. It's like, how do we actually implement this to further the business? And I think that's going to be the question over the next year, is how do we actually leverage AI in a profitable way? And I think whoever can do that in the next year is going to be.
Okay, thank you very much. I think we are just in time to take a few questions from the audience.
Hi, thank you very much for the discussion. Very insightful. So my name's Tim Hunter. I work for a company called Code Metal. And we work with the US Air Force and defense primes like L3 Harris and Raytheon to effectively help accelerate the embedding of prototype code onto bare metal, or the migration between heterogeneous compute targets between, let's say, CUDA and OpenCL, so that they do it much faster. And we actually use AI validation and verification techniques to prove behavioral equivalence and apply formal methods and automate test generation and things like that to accelerate time to market for our customers. It sounds like what we're doing is very much aligned with a lot of the challenges I think we're hearing that are experienced in the automotive industry. I suppose my question to the panel is, how open are you to adopting technologies that don't originate from the automotive industry and maybe come from the government or US defense space, like where my company primarily works?
Yeah, again, I'll take a stab at it. I think it's very much a possibility, because the automotive space is moving so quickly these days that it cannot be developed everything specific to the automotive. Like from the networking standpoint, just because we were talking about Ethernet a few minutes ago, we completely absorbed the IEEE specs onto that. We just customized it to some extent, but most of the meat and bones are coming from those spaces. So if there is other areas that actually can give us the same robustness and can give us a real-time based I'll say constraints that we can enforce on it, I think I see that a very fair possibility.
Sounds good.
Yeah, let me add something, because what you're bringing up here is an extremely important point, and I think this is the key driver, at least for autonomous driving in the business where I am. If we would follow every process which is established in the automotive industry, we will never get an autonomous vehicle. And let me just say a couple of things why. This whole AI technology is coming from a completely different domain than from automotive. This is absolutely not related at all. And now let's be even more precise here. One of the key enablers is this transformer-based stuff, the large language models which are out there. ChatGPT, now Anthropic. The basic functionality of those models we are using for our behavior stack. And now let's just very briefly talk about ISO 26262, for example. The automotive standard, it's very hard to comply to that. So in a summary, actually I would say what we are doing here with the AI-driven vehicle is way more coming from different technology spaces than from automotive. And just one more last statement. The big event in autonomous driving was the DARPA Urban Challenge like 20 years ago, and that was organized by the defense department, actually. Yes. So this was the baseline and the kickoff for everything what we have done so far.
Nice. We have another question there.
Yeah, good morning. Thank you very much. My name is Dirk Sebam. I'm working for TRI-Optics, and in terms of the optical industry, in the past that was always driven by better lens qualities, better optical performance, and the industry was requiring higher resolutions, so the sensor resolution needs to increase all the time. And the optical side was driven by this, by getting better optical performance, better image quality. So now I'm wondering, in what we learned today in context versus the object or AI-driven, in terms of the performance, the resolution, are we already across a pivot point that says, no, we don't want more resolution, we already had enough data, abundance of data, computation is rather critical than getting more data, and AI can live with less data, with less optical quality than in the past when it was coming from photography, for example. So that would be very interesting to me. Are we across the point already? Do we have enough quality, enough resolution, or does AI still require more information?
Anyone would like?
I'll try to answer. I think in terms of resolution, I think it might be pretty mature. We are more talking about the contextual side of it. I think there is nothing called like enough data, I would say, because it's still like the detail is very long. So I don't think we can able to produce the 100% effective data. Rather than, I think we should go for a more contextualized data. So in terms of like, for example,
this networking coffee break is supported by Gentex and ST Microelectronics.
Sorry. So for the optical performance in this case, I would say the sensors should be, we should go for the, like for example, when we are talking about the logging of the data related. So in this case, more on the different failures and the environmental failures, other things should be contextualized so that the models can able to have the scenarios where they can like a group long tails rather than providing the entire data of the long tails. I hope I touched somewhere towards your question. Or
I saw Pranit wants to add something.
Yeah, sorry about that. Yeah, because I work on the sensor side, right?
Yes.
It depends on who you ask. If you ask perception, they always want better quality, right? However, what I'm also seeing is a lot of this is creating new annotation methodologies, right? Like it's no longer the bounding boxes that we are looking for.
Yes.
As we are going into more and more gray areas into how the data is extracted, there is absolutely more requirements in some of these areas. But are you always going to like a 12 megapixel or an 8 megapixel? Depends on who you ask, because there are other parameters about reliability and other things that some of these teams care more about. So I would say, as Venkat mentioned, maybe we are quite mature. Maybe the progress could be a little more slower at this space, but again, it completely depends on who you ask.
And to me, it can be also, I mean, the sensors can do already more than what our sensors do. Is it that we build better AI for LiDAR that is still immature with respect to what we have for camera and so on.
Correct. Yeah. So as a group, I think we are at a really good place from where everyone is pitching their orthogonal perspective.
Mm-hmm.
But when we're talking about degraded states, that is where the burden falls more on a particular optical or an RF technology, where there is always, hey, what if we get more, right? And that is where the challenge is starting to emerge.
Okay, so I think we are running out of time, but I would like really, really sincerely all the panelists, Martin, David, Pranit, and Ventak, because I think the discussions were really exciting, and there is still a lot of work to do for AI validation, so maybe we will see each other next year again. Thank you.
Thank you all.
Thank you.